everyone! So today, for the 7th day of Christmas, we will be evaluating this integral right there, namely the integral from 0 to pi over 2 of x squared over the sine of x dx. And it's actually a really nice integral because the answer has not just one, but 3 fundamental constants of mathematics. So it's going to be an intense ride. Okay, so let's start. So first of all, what we'll do is we will recall the exponential definition of sine. So we know that sine of x is nothing but e to the ix minus e to the negative ix all over 2y. And now what we can do is, we can just take the reciprocal and then plug this into our integral, factoring out the 2y. So we get 2y integral from 0 to pi over 2 of x squared over e to the ix minus e to the negative ix. And then next step is to expand this fraction by e to the negative ix. So we have 2i integral from 0 to pi over 2 of x squared e to the negative ix over 1 minus e to the negative 2ix. And now, next step is to use the Maclaurin series expansion for 1 over 1 minus x. So we know that 1 over 1 minus x is just the sum as n goes from 0 to infinity of x to the n with some convergence criteria that we don't care about here. So we have, do I have the space to write everything? No, I'll write this on the second line. So we have 2i integral from 0 to pi over 2 sum n goes from 0 to infinity of, so we have x squared and then e to the minus ix times, okay, so we have a 1 there, and then we have e to the negative 2ixn, so factoring out the negative ix, we have 2n plus 1, so we have this thing right there. And now, interchanging the integral sign and the summation, which we can probably do because reasons, we have 2y sum as n goes from 0 to infinity of integral from 0 to pi over 2, of x squared e to the negative ix times 2n plus 1 dx. And now our next step is to integrate this thing. But this is nothing too fancy, just integration by parts, but you really have to focus on what you're doing. Because if not, you're going to make plenty of mistakes, like I did while recording this. So we have actually I'll call this integral I1. So yeah, I1 will be, so as I said, we'll use integration by parts. So yeah, plus minus, yeah. So we'll differentiate x squared because when we differentiate it, we get 2x and then 2 and then 0. And we'll integrate e to the negative ix times 2n plus 1. Integrate this once, we get e to the negative ix over 2n plus 1 over the exponent but without the x. So negative I times 2n plus 1. But then expand this fraction by I over I. We'll have an I in the numerator, and then in the denominator we'll have negative I times I, which is just 1. And now if we integrate this again, we get e to the negative ix times 2n plus 1 all over the exponent without the x but squared. So negative 1 squared is 1, I squared is negative 1, so we'll have a negative sign in the front. Hold on. No. It's because my negative sign is connected to my fraction ball. Thank you. And then, yeah, 2n plus 1 whole thing squared. So 2n plus 1 squared. And then integrate this again. So we have e to the negative ix times 2n plus 1 all over the exponent without the x, but this time cubed. So we have negative 1 cubed is negative 1. I cubed is negative I, so we'll have an I in the denominator times 2n plus 1 whole thing cubed. And then multiply this by I over I, so we'll have an I in the front. And then we'll have I squared in the denominator, which is just negative 1. So yeah, just do the usual integration by parts stuff. And we don't really need to integrate the last line because it's just 0. This will just be a constant and we don't need that, so we have. Also, we'll factor out the constants to make things easier, so we'll have I over 2n plus 1, x to the n e to the negative ix times 2n plus 1, evaluated at 0 and pi over 2, and then minus minus, which is plus, 2 over 2n plus 1 squared times x e to the negative ix times 2n plus 1, evaluate this as 0 and pi over 2, and then minus, because this is plus minus, 2I over 2n plus 1, this time cubed, and we have e to the negative ix times 2n plus 1, evaluate this at 0 and pi over 2. Okay, so what can we do now? So plugging 0 into here, we get 0 squared, which is 0 times anything, which is 0. 0 times, plugging into here, we get 0 times something, which is 0. And we can use the negative sign to change the bounds at which we evaluate things. So we'll evaluate this at pi over 2 and 0 instead of 0 and pi over 2. And then we have to evaluate things, which is going to be a mess. It is already a mess, but it's still going to be a mess. So let me make a box around there. And let me leave myself some space, because if you notice, 3 of the 4 terms that we'll get when evaluating things will have a factor of e to the negative I pi over 2 times 2n plus 1. So let's evaluate this thing. So e to the negative I pi over 2 times 2n plus 1 is... Okay, so e to the negative I pi over 2 is, if you go along the complex plane, we'll have magnitude of 1, and then negative I pi over 2, so we land at negative I, so we have negative I times to the power of 2n plus 1. And then this can be split as negative 1 to the 2n plus 1, which is negative, because that is an integer, times I to the 2n plus 1. So we have negative I to the 1 is I, and I to the 2n is I squared to the n, which is negative 1 to the n. Sorry. And overall, we have negative I times negative 1 to the n. So, if we plug things in, we get... Okay, so plug this in there, we have pi squared over 4 for the x squared times I. And we have negative I times negative 1 to the n over 2n plus 1. I times negative I are going to cancel, so we have negative 1 to the n over 2n plus 1 times pi squared over 4, obviously. And then we have plus 2 times pi over 2 is just pi. And then we'll have the denominator of 2n plus 1 whole thing squared. And we'll have a negative I times negative 1 to the n. So the negative can be dragged to the front. So we have minus pi I times, well, this. And then plus, plugging 0 into here, e to the negative I, blah, 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 is going to turn into e to the 0, which is just 1. So we have 2I over 2n plus 1 cubed. And then we have minus 2I over 2n plus 1 cubed times negative I times negative 1 to the n. I times negative I is just 1, so we have 2 times negative 1 to the n over 2n plus 1 cubed. Let me just check that I did not make any mistakes there. I think we're okay. So therefore, our integral, which I'll denote as I, so yeah, our integral I. So our I will be, well, we just plug this into our summation and then distribute the summation sign. So we'll have I is equal to, okay, so we'll have pi squared over 4 times 2I, which is pi squared over 2 times I, times the sum as n goes from 0 to infinity of negative 1 to the n over just 2n plus 1. So 2n plus 1, and then minus, so okay, so we have 2I times negative pi I times negative I is 1. So we just have plus 2 pi, yeah, plus 2 pi, sum as n goes from 0 to infinity of negative 1 to the n over 2n plus 1 whole thing squared. And then 2I times 2I is negative 4, so just negative 4 Yeah, exactly. Negative 4 sum as n goes from 0 to infinity of 1 over 2n plus 1 whole thing cubed. And then minus 2i times 2, which is 4i. So minus 4i sum where n goes from 0 to infinity of negative 1 to the n over 2n plus 1 whole thing cubed. And now, next step is to clean up the board, obviously, and evaluate each of these summations separately. Okay, so now that I've cleaned up this board, we can continue with our integral, which is currently quite a mess of series, but it's going to get nice in a second. So, first, this one. This series is actually the Taylor series expansion for arctan x at x equals 1. So this is just arctan 1 or pi over 4. And then this second series, well, this is just Catalan's constant, because it is, because that's literally the definition. This series is, we'll come back to that. And this series is actually a very famous result. It is precisely equal to pi cubed over 32. I won't go into any detail on how to evaluate this series there because it's quite long, but I'll link somewhere, probably in the description, to a video from Flammable Maths a while back who evaluated this sum using Fourier series, so that was pretty nice. And yeah, I said I was going to come back to this sum, so I'll call this sum S. I'll use red. So, this sum S. So S is equal to, we'll expand it like a few terms, just two. Yeah. So we have 1 over 1 cubed plus 1 over 3 cubed plus 1 over 5 cubed plus so on, so on, so on. And then what we will do is we will add in all of the missing even terms and then subtract them back. So we have 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed plus so on up until infinity minus 1 over 2 cubed plus 1 over 4 cubed plus 1 over 6 cubed plus so on, so on, so on up until infinity. And now, here 2 cubed can be rewritten as 2 cubed times 1 cubed. 4 cubed can be rewritten as 2 cubed times 2 cubed. 6 cubed can be rewritten as 2 cubed times 3 cubed. And so on, so on, so on. So what that means is all of our terms in our second series have a common factor of 1/8. So we can factor out that 1/8. And then the remaining two series are just the same. So it will be 7/8 times that exact series. But this series is just Apéry's constant, the Riemann zeta function evaluated at 3. So yeah. So now if we plug everything in, we get that our I is equal to, so we have, here we get pi cubed over 2 times 4, which is 8, multiplied by I, plus 2 pi g, Catalan's constant, minus 4 times 7/8, which is 7/2, zeta of 3, yeah, that should be it. And then minus 4 over 32 is 1/8, so pi cubed over 8i. And then pi cubed over 8i minus pi cubed over 8i is just 0. So all of these cancel out, which is understandable given that our integral has nothing to do with complex numbers. It is a purely real function, well, over that interval. So we have an answer of, actually let me write this in full because it's a nice answer. Therefore we have that the integral from 0 to pi over 2 of x squared over sine x dx is, ladies and gentlemen, and everything in between, 2 pi Catalan's constant minus 7/2 zeta of 3. This was a mess, but it turned out pretty nicely. As I said, 3 fundamental constants of mathematics in one answer: pi, Catalan's constant, and Apéry's constant. So yeah, that's a pretty nice interval. And yeah, so this video, and of course, not Merry Christmas because it was too long, but Happy New Year in advance.